Every turn of a ball bearing concentrates load into contact zones small enough that geometry matters on a microscopic scale. The ball looks simple, but its diameter, spherical form, surface finish, material stiffness, and the race around it all meet at the same moving contact. A zirconia-bearing ball is a precision zirconium oxide rolling element, not a grinding bead. Inside a bearing, it must roll repeatedly between raceways while keeping its contact surface stable. That makes the material only half the story. The sphere also has to be ground, polished, graded, and matched as a bearing component. For this component family, the specified Vickers hardness reaches up to 1200, depending on material grade. A hard surface helps resist wear that can disturb the polished contact track. In a bearing, preserving that surface geometry supports more stable rolling contact over repeated cycles. Zirconia is unusual among oxide ceramics because it combines high hardness with comparatively high fracture toughness. That does not make a ceramic ball immune to impact or overload. It means a correctly manufactured ball can offer stronger resistance to crack extension than many oxide ceramics when repeated contact stress or handling damage acts on an existing flaw. The non-metallic zirconium oxide surface is also electrically insulating and non-magnetic, and dense zirconia is resistant to many wet and chemically aggressive environments. Those features become useful when rust, current pads, magnetic response, or metallic contamination are engineering concerns. Chemical compatibility still has to be checked against the actual medium and temperature. Once the ball enters a bearing, the load is transmitted through small Hertzian contact regions between the sphere and the raceway. The stress field repeats every revolution. That is why a microscopic flat, scratch, diameter mismatch, or local surface defect and matter far more than its visual size suggests. Precision grade is a geometry language, not a hardness rating. Within this zirconia ball range, options from G5 through G200 can be reviewed. The grade number is used to control limits associated with ball diameter variation, spherical form, batch consistency, and surface quality. Lower grade numbers represent tighter geometric control. Roundness and surface finish work together. The sphere must distribute contact consistently as it rotates, while the polished surface should avoid introducing unnecessary roughness into the raceway contact. In precision bearing systems, ball geometry must be matched with race groove geometry, internal clearance, lubrication, load, and speed rather than selected by diameter alone. The diameter range available for this family extends from 0.4 millimeters to 63.5 millimeters. It includes very small metric balls, common bearing diameters, and inch-derived sizes such as 3.175, 6.35, 12.7, and 25.4 millimeters. The correct diameter is determined by the bearing geometry, not by the ball in isolation. A non-standard requirement may involve more than a custom diameter. Precision grade, lot diameter variation, spherical form, surface finish, material grade, and the mating raceway all affect the final assembly. For replacement work, the original ball size, race material, internal clearance, load direction, speed, lubricant, and operating medium should be known before the geometry is changed. One representative application is the low-load bearing system in corrosive or media-lubricated fluid handling equipment. In that environment, 4 zirconia advantages can be relevant: corrosion-resistant rolling contact, electrical isolation, non-magnetic response, and a hard polished surface. Zirconia is not chosen simply because the environment is difficult. Contact pressure, rotational speed, race material, lubrication regime, contamination, temperature, and chemical exposure still define whether the bearing system is suitable. Engineering references place zirconia rolling elements particularly in lower load, corrosive, dry running or media lubricated contexts, while other duty profiles may require a different bearing material strategy. In a bearing, the ball is one of the smallest parts carrying one of the most concentrated contacts. Hardness protects the surface, toughness helps control crack growth, corrosion resistance protects the interface, and precision grinding controls how the sphere meets the race. Smooth rotation begins before the first revolution. It begins with a ball whose material, geometry, and operating conditions belong to the same load path.